Chapter 5. Collective motion. Brief mention will now be given to collective motion for idealized cases such as rigid bodies and simple material bodies, with the phenomenological discussion involving material bodies partly left to Chapter 8 Phenomenology and Dimensional Analysis. This brief review starts with rigid body motion. 5.1 Rigid body motion. For a rigid body, all of the internal loadings are net zero. If the geometry of a rigid body is static, then forces applied must be balanced and transmitted through the rigid body such that the net forces and torsions are net zero. At any position in the body, we can evaluate the net forces and moments of force according to 6 scalar equations of equilibrium. The sum from 2 of f sub x equals 0, the sum from 2 of f sub y equals 0, the sum from 2 of f sub z equals 0, the sum from 2 of m sub x equals 0, the sum from 2 of m sub y equals 0, the sum from 2 of m sub z equals 0. Equation 5-1. When speaking of a homogeneous material comprising the rigid body, it is possible to speak of the average normal stress to a cross-sectional surface sigma equals n divided by a, where n is the internal axial load and a is the cross-sectional area, and the average shear stress to a cross-sectional surface, tau sub avg equals s divided by a, where s is the shear force acting on the cross-section a. Let's consider some classic problems from Hibbler to work through some of these statics issues and see their application.
Example 5.1. Hibbler 1-12. A beam is held horizontally with its left end at a wall-mounted pin, point A. Proceeding left to right along the beam, we have points labeled as follows. 1 foot to the right of A there is point D, another 2 feet and point B, another 1 foot and point east, another 2 feet and point G, and another 1 foot to reach the end where a load is indicated due to a cable connection at 30 degrees outward, rightward, from the vertical. At point B is a support beam, directed upwards to the wall, forming a 3-4-5 triangle with the wall, upper pin mount labeled C, where the 3 corresponds with the 3 feet from A to B. The load on the cable is 150 pounds. There is also a uniform distributed load between point B and the end of the beam of 75 lb divided by F of T. Along the diagonal support beam, down 1 foot from the support pin at point C, is an internal beam point labeled F. Determine the resultant internal loadings at cross-sections at points F and G on the assembly. Consider the free diagram for the horizontal beam. This will allow us to solve for the axial beam force F sub CB from which the internal loading at F can be trivially obtained. A cut sectioning to a free body at the cross-section of G is taken to the right side for another simple free body analysis to get the internal loading at G. First, for F sub CB.
See the next equation. From this we have to the internal load at F. See the equation shown. Let's now consider the internal loading at G by way of the free body section, C for details, consisting of the body on the right side of the cut. See the next equation.
See the equation shown. Exercise 5.1. Redo with 150 pounds 250 pounds. Example 5.2. Hibbler 1-66. A frame is formed by a vertical wall and 2 beams coming together to form a 3-4-5 triangle, hypotenuse upwards, so beam under tension, not compression. The wall mounts are hinged pins, as is the connection between the beams. The distance between the wall mounts, vertical length, is 2 m and the horizontal beam has length 1.5 m. The lower wall mount is labeled point A, the upper B, and the connection point of the beams is point C. Thus, the hypotenuse is length BC. At point C, a load P is indicated vertically downward. Cutting through beam BC vertically is indicated a cross-sectional cut labeled AA.
Determine the largest load P that can be applied to the frame without causing either the average normal stress or the average shear stress at section AA to exceed sigma equals 150 MPa and tau equals 60 MPa, respectively. Member CB has a square cross-section of 25 mm on each side. Let's start with consideration of the horizontal beam as a free body to obtain F sub BC in terms of P. See equation 5-2. The cross-section under consideration is not orthogonal to the axis of the beam, thus need to correct the normal force and non-zero shear force accordingly. See the next equation. The area of the cross-section is a sub AA equals a divided by the cosine of theta equals 5 divided by 3 times A. Thus, the normal stress to the indicated A cross-section is maximal when at the stress limit indicated.
See equation 5-3. The maximum load P that can be according to the normal stress is limited to be P sub max equals 208 kN. The shear stress indicated at A can be at most 60 MPa, from which we calculate. See equation 5-4. The maximum load P that can be according to the shear stress is limited to be P sub max equals 22.5 kN, and since this limit is reached sooner, the maximum load possible at P is 22.5 knots, to avoid shear failure. Let's consider some dynamical situations with rigid bodies. A few have already been mentioned, but with idealized massless rods. Exercise 5.2. Redo with sigma equals 250 MPa.
Example 5.3. A plank leaning against a wall. Let's consider the problem of a plank leaning against a wall. If the plank makes an angle theta sub 0 with the floor initially and the plank is free to slide along the floor, no friction, what is its motion? When, if ever, does the plank leave contact with the wall? When, if ever, does the plank leave contact with the floor? This is similar to problem 3.18 on page 85 of, with plank of length L and mass m. To begin, recall that the moment of inertia of a uniform plank about its center of mass is I equals 1 over 12 ml squared. The kinetic energy term can then be given in terms of the center of mass linear motion and the rotation about that center. See the equation shown, where the x, y, coordinates of the center of mass are related to theta by x equals L over 2 cosine theta and y equals L over 2 sine theta, while maintaining contact with the wall. The potential energy is simply V equals mg of y. The Lagrangian is, thus,
see the next equation. The Euler-Lagrange EL equation for the latter, constrained form then gives. See the equation shown. Since we are interested in the contact constraints, and when they fail, let's revert to the initial form, and add Lagrange multipliers for the constraints. See the next equation. The equations of motion for the x, y, coordinates of the center of mass and the lambda tau Lagrange multipliers for the x constraint are.
See the equation shown, where the tau multiplier goes to 0 when 3 have sine theta sub c minus sin theta sub 0 equals 0. Thus, the plank leaves the wall when the contact point is at height. See the next equation. At the instant the latter leaves the wall, the x-coordinate is free and has.
See the equation shown. Let's now examine the y constraint before and after the plank leaves the wall. See the next equation. Before the plank leaves the wall we have theta squared equals 3g over L times the sine of theta sub 0 minus sine theta, and theta equals negative 3g over 2L cosine theta, for which lambda is greater than 0 always. After the plank leaves the wall we have theta squared equals g over L the sine of theta sub 0 and theta equals 0, for which lambda is greater than 0 always. Thus lambda never goes to 0, and the plank never leaves the floor, with COMY motion similarly expressed as with the x motion above. Exercise 5.3. Suppose there is a worker on the ladder at midpoint of mass m. Repeat the analysis.
Example 5.4. Revolving pipe at fixed angle with ball inside. Consider a pipe that revolves with constant angular velocity omega about a vertical axis, forming a fixed angle alpha with it. Inside the pipe is a ball of mass m that slides freely without friction. Using spherical coordinates, at time t equals 0 let the ball position be r equals a and d r over dt equals 0. For all times of interest the ball remains in the upper part of the pipe. A. Find the Lagrangian. B. Find the equations of motion. C. Find the constants of the motion. D. Find t as a function of r in the form of an integral. Solution. A. The Lagrangian for the ball's motion is given by. See the equation shown, where, for spherical coordinates, ds squared equals d r squared plus r squared times d theta squared plus sin squared theta d phi squared. Thus,
see the next equation. And we get. See the equation shown. B. The equation of motion for r for fixed rotation frequency and specified angle of declination. C. The constant of the motion is thus. See the next equation. From R equals A and dr over dt equals 0 initialization we have.
See the equation shown. D we can write. See the next equation. Or, switching to integral form, see the equation shown. Thus, see the next equation.
Exercise 5.4. Repeat analysis for a revolving paraboloid curved pipe with ball inside. 5.2 Material bodies. Thus far we've seen how to compute stress as a force over an area, sigma equals F of slash A. With non-idealized bodies, such as rigid bodies, i.e., material bodies, there will be a response, a deformation, to this stress. To quantify this deformation, let's define strain. See equation 5-5. The relation between applied normal stress and resulting strain deformation is given by Hooke's law. See equation 5-6, where y is a constant appropriate to the material under consideration known as Young's modulus. From this we can compute the strain energy density, U equals sigma epsilon divided by 2. Similar relations exist for shear stress. If we consider a constant load and cross-sectional area, we can group the equations to get a relation on the change in length for given applied, normal force.
See equation 5-7. If there are connected sections with different areal cross-sections, etc., their delta S are additive. Lastly, for this brief overview of material bodies, is to account for thermal stress. Most thermal effects are not discussed until. It is well known that material bodies expand or contract under change of temperature. This is described by the following. See equation 5-8, where alpha is the linear coefficient of thermal expansion.
Example 5.5. Hibbeler, 3-8. A beam is held horizontally, initially, with length 10 f of t, and a distributed load on its entirety of W. It is held at one end by a wall-mounted hinge pin and at the other end by a guy wire support at 30 degrees to the horizontal. The rigid beam is supported by a pin at C and an A36 guy wire AB. If the wire has a diameter of 0.2 inches, determine the distributed load W if the end B is displaced 0.75 inches downward. We need to first compute the strain on the guy wire and from this determine what load is present. The original length AB is 11.547 feet. The stretched length of the guy wire is 11.578 feet, thus the strain is epsilon equals 0.00269. The Young's modulus for a 36 guy wire is 29 times 10 cubed ksi, thus have. See the equation shown. Exercise 5.5. Redo for wire diameter 0.3 inches, and displacement of NB is 1 inch along length AB.
Example 5.6. Hibbeler, 4-70. A rod is horizontally mounted between two walls by use of two identical springs on either end, between the wall and the rod's ends. The rod is made of A992 steel. Alpha equals 6.6 times 10 to the negative 6 power divided by degrees Fahrenheit, and has a diameter of 0.25 inches. If the rod is 4 feet long when the springs K equals 1000 lb divided by IN are compressed 0.5 inches, and the temperature of the rod is T equals 40 degrees Fahrenheit, determine the force in the rod when its temperature is T equals 160 degrees Fahrenheit. From delta sub T equals alpha normal triangle TL vector delta sub T equals 3.168 times 10 to the negative 3 power F of T. With the two springs acting together, we have the force acting inward on both sides of. See the next equation. Exercise 5.6. Repeat for T equals 360 degrees Fahrenheit and spring compression 0.75 inches. 5.3 Hydrostatics and stationary fluid flow.
Hints of special relativity, Fizeau, the relativist Doppler effect, and the bond decay calculus. Special relativity is revealed when going to field theory to describe EM. Hints of the existence of SR for consistency Sake are seen in primitive early experiments with light, but significance not understood at the time. Fizeau 1851 found that the speed of light in water moving with a speed v, relative to the lab, could be expressed as. See equation 5-9, where the dragging coefficient was measured to be k equals 0.44. The value of k predicted by Lorentz velocity addiction, See equation 5-10. Treating light as a particle, the laboratory observer will find its speed to be.
See the equation shown. Water has n approximately equals 4 divided by 3. Thus, U sub x approximately equals c over n plus 0.44 times v. Thus agreement with the experiment done in 1851.